Welcome to the first podcast on 4.4 wave behaviour, part of IBDP Physics Topic 4, waves and oscillations. It's quite a big one, looking at reflection and refraction, so we will go through it rapidly as we can. So as a new section, we'll be looking at reflection and refraction, and we'll be looking at Snell's Law, which is, spoiler alert, the equation at the bottom of the page there. And we'll be going through quite a few different skills, including looking at boundaries, solving problems involving reflection at a plane interface, solving problems involving Snell's Law, and determining refractive index experimentally. So again, we can use water waves as an example of the process, although again, one of the essential ideas here is that pretty much everything we apply to waves can be applied to all sorts of waves. So here you see an example of water waves on the surface, and you can just make out that water waves are reflecting. So reflection is one of the four things, reflection, refraction, interference and diffraction, that basically all waves do. Now, how do you know you have a wave? Well, one of the ways you know you have a wave is if it does these things. So looking at that sort of from above, hopefully these images, this symbology is familiar from previous sections. We have an incident ray, we have a reflected ray. So these rays, you remember, just show the path of a little bit of a wave, the energy of a wave, so to speak, and the red and yellow lines are the wave fronts from the incident and reflected waves. And you'll see that as they overlap, they will be interfering, which is what you can see happening from there, using superposition to see what's actually happening in those cases. But what we actually care about in this case, well, the question we're trying to ask is, okay, if we know where the incident ray is, where will the reflected ray go? And the way we can do that is we can define something called the normal. So the normal is a line that we draw, and this is at a right angle to the surface at the point where the wave hits that we care about, the bit of a wave that we care about hits and reflects from the barrier. If, by the way, we had, instead of a plane surface, we had a curved surface, that's not too difficult if we're just interested in one little bit of a wave, because we can draw a tangent and see what happens. And the law of reflection is pretty simple. You probably looked at this when you were younger. It's that the angle of incidence measured between the incident ray and the normal is equal to the angle of reflection measured between the reflected ray and the normal. A more difficult process is refraction. Refraction is the bending of waves. The reason that waves bend is because they change speed. So here on the right hand side you can see a photograph showing this in action, a Google image showing waves bending as they approach some land. And the reason they're doing that is because the water depth is changing. As water depth changes for water, the speed of wave changes, and it's the speed of wave that's very important. An analogy here, which is quite common, is to imagine you have a marching band or something marching from the bottom of this image to the top, looking down at it, and they're going from concrete to sand. And every marcher keeps pace with the people to the left and right of them. And as they cross from concrete to sand, they go slower, because you can't march so quickly through sand or on sand as you can as you're walking on concrete. But because the boundary is not aligned with the marchers, they're marching in one direction, but the boundary goes to the player on the right, the clarinetist on the right, starts moving slower, quicker, earlier compared to the clarinetist on the left. And the effect of this will be that they change direction. Okay, so they will go from going straight ahead, bending towards the right. And we can draw the normal, and they will be now moving away from the normal, towards the normal. Sorry. We can draw this from above. Similarly, So this would be waves, this could be water waves travelling from fast to slow, but it could also be light waves. And when we talk about refraction, the experiments that we do in the IBDP physics course tend to more commonly be talking about light than we are talking about water, but the same rules apply to both. So you have waves coming in, you have waves going out there. Notice that as the speed changes, so does the wavelength of the waves. They get closer together. The frequency doesn't change. The number of waves arriving and then departing a point doesn't change, but the speed gets slower. C equals F lambda. If C gets slower and F has to stay the same, for every wave arriving, a wave has to leave, then the wavelength will decrease. And we can set up similar terminology as before. We have the angle of incidence as it was before. We have a normal in the same place it was before. It's drawn perpendicular to the boundary at the point of impact. And we have the angle of refraction. We'll call this theta 1 and theta 2. We use that because that's what it uses in the data booklet, in the equation that the IB gives you. We have V1 is the wave speed, the speed of wave in medium 1, and V2 is the speed of wave in medium 2. And to predict the relationship between theta 1 and theta 2, we use something called Snell's Law. So it's a little bit more complicated than the law of reflection. The law of refraction, or Snell's Law, is that sine of theta 2 divided by sine of theta 1, the ratio, is equal to the ratio of the speed of a wave in the two media. Now, to help us deal with this, we can come up with a term and we call it refractive index, or the absolute refractive index. The absolute refractive index is a ratio of velocity of light in a vacuum relative to the velocity of light in that medium. You may recall we've talked about the velocity of light, and you may well remember that the velocity of light is a constant, about 3 times 10 to the 8 meters per second. That's true, but that's only true in a vacuum. In any other transparent media, the speed of light is slower. Some common values of refractive index for air are 1.003, which is very close to that of a vacuum. And in fact, certainly at this level, if we're doing experiments, we don't need to do experiments in a vacuum. We don't need to worry about the fact it's air, not a vacuum. We can generally just use the speed of light as being the same in both. However, for water, for other liquids, it changes. For glass, about 1.5 is typical. Diamond is a good example to use because it has about the highest refractive index that we might encounter of 2.42, which is a lot. Light travels a lot slower in diamond than it does in a vacuum or in air. And we can change Snell's law now to the full version that the data booklet gives you, which is that N1 divided by N2, the ratio is same as theta 2 divided by theta 1. So it's N1 over N2, but it's V2 over V1, and theta 2 over sine theta 2 over sine theta 1. Remember, it's the different way around. The Oxford textbook, by the way, in at least one place, puts that the wrong way around. So, Snell's law, refractive index, put the full version in there. Let's have a look at an example. We have an incident ray coming in at 30 degrees from the normal, from air through to glass. If that's the speed of light in air, then that's the speed of light in glass. But as we've seen, we don't need to worry about that. We can just use the refractive index instead. We can have M1 equals 1.003, which is pretty much the same as M1, and N2 equals 1.5. Plug those into the Snell's law equation. 0.66 is sine theta 2 over 0.5, which is sine 30 degrees. Rearrange, sine theta 2 equals 0.333, so theta 2 must be sine to the minus 1, 0.3 recurring, which is about 19.5 degrees, which is about right. It fits what you can see. Don't forget, when you're going from low refractive index to high refractive index, when you're going from fast to slow, the ray will always bend towards the normal. It's the opposite way round, of course, if you're going in the other direction. If you're going from slow to fast, from high refractive index to low refractive index, the light ray will bend away from the normal. This reversibility is very useful though, because it means you can use the sort of same equation for both. You just have to work out what direction it is that you're interested in. Experimentally, we can determine the refractive index quite simply. We use a prism. We've used a semicircular prism in this case because it just makes life easier, because you only have to worry about refraction at one boundary, not at two boundaries, because when it leaves the prism, it's travelling already at 90 degrees relative to the boundary, and therefore carries on moving straight. Instead of using a solid block of material, you could use a container. If you wanted to, say, measure the refractive index of a liquid, use a prism container and fill that container with the liquid. So adapting Snell's law, n1 over n2 equals sine theta over sine theta 2 over sine theta 1. But as we've said, air, vacuum, pretty much the same thing. So let's just put a 1 there for n1. So n2 equals sine theta 1 over sine theta 2. So rearranging, n2 equals sine 50 degrees over sine 35 degrees. That's 50 degrees there, 35 degrees there, which gives us these values, which gives us a refractive index for this material of about 1.36, from which I can conclude that this is probably a plastic block rather than a glass block. I would expect the refractive index of glass to be a little bit higher. Okay, we looked at that before. So wave behaviour, so reflection and refraction, Snell's law, solving these problems, determine the refractive index experimentally. I think we're done.